Okay, so welcome back, everybody. We're very happy to have Anastasia Volovich, who will tell us about scattering amplitude and cluster output.
Great. Okay, so it's great to be here. Thank you very much, Matteo and Lauren, for having me. Okay, so yeah, I'm going to tell you a little bit about scattering amplitudes and cluster algebras. So the plan of my talk is as follows. I'm going to start with a brief review of n=4 Yang-Mills theory amplitudes. So you heard a little bit about them from Yara's talk. So I'm going to tell you a little bit about the status, how much we've computed, what tools we're using, and what the structures we are finding, and what some of the problems are. And let me just say right away, so for the talk, I'm going to be talking about the integrated amplitude. So when you compute scattering amplitudes in physics, you have to do an integral. And so there are various techniques to write down the integrals that contribute, but then you have to do the integral. And the integral is usually hard. And so I'm going to be telling you about final answer of that, final result of that integral. For example, what you heard from Yara was Amplituhedra, which is about writing down an integral, but you have to perform an integral, which is a very hard task. So that's what the focus of my talk will be. So the second part, I will tell you a little bit about some of the recent work. And to be precise, I'm going to focus on the arguments of these scattering amplitudes. So again, I will tell you in great detail what exactly I mean here. And those arguments are going to be explained. Explained by something called symbol alphabet, which you heard a little bit from Yara already. And I'm going to, the problem that I will be focusing on is how to derive those arguments of scattering amplitudes or the symbol alphabet to all loop orders. Okay, so, and I will, again, hopefully explain everything. Symbol alphabets are what ziggurat graphs are, everything that, so please interrupt me at any time. So in my talk right away, in my talk, I'm going to be focused on 6 and 7 point amplitude. So when you talk about scattering amplitudes, as Yara explained, you have, for example, two particles come in and 4 particles come out. That's what I call 6-point amplitude. And 7-point amplitudes is, so n stands for 6 and 7. And then after me, Mark is going to focus more on n = greater than 7, so 8 and 9, etc., etc. Okay, so that's a plan. All right, let me start with some of the review. Again, Yara already gave a beautiful talk on n=4. He's happy and smiling, and yes, it was a very nice talk. And he already explained to you why n=4 Yang-Mills theory attracted so much attention. But nevertheless, let me say again. So we like this theory a lot. I'm not going to tell you all the details about this theory because the amplitudes in this theory have amazing structure. So there are extra symmetries, such as, again, these are just to throw out some words, such as dual conformal symmetry, Youngian symmetry, relation to cluster algebras, relation to polytopes, to tropical geometry. All of these structures are for this particular theory. And this is a theory which is best understood out of all quantum field theory at present time. And our goal in physics is to try to generalize it to more realistic theories that, we can, such as standard model of physics, which we can test at gliders. So it's a simple model that likely can be solved exactly. And but everybody was hoping to solve it for the past 15 years. So still working on it. And it provides a lot of general intuition and tools for more realistic theories. So a lot of the tools, some of the tools that I will be describing in my talk have been generalized to other theories. So, but for now, let me just say that here we stop. This talk is going to be about n=4 Yang-Mills theory. And for the, so as part of the something called snowmass process, this is when particle physicists collect sort of ideas and make plans of what they want to do for the next, was it 5 years or 10 years? we wrote up some highlights of this whole research program in this paper. So this is probably, I think this is probably the most, can you see this pointer? Yeah, this is probably the most recent review on this that I recommend to all of you. Okay, so before I start talking about all the structures and methods, let me just say that in physics, we should not forget what we're after. So in this whole Amplitudes program, we want to do two things. So the goal of the program is a twofold. On one hand, we want to, we would have some theory, some quantum field theory, in this particular case, n equals 4 Young-Mills theory, and we would like to explore the rich and beautiful mathematical structure in this theory. But that's not all that we want to do. We want to use the structures to do something else. We want to use these structures to be able to compute something that was not possible to compute with the previous method. So this is like a litmus test. So there's a lot of talk and structures and this, but you really, no serious QCD person is going to like listen to any of that unless you can come and say, okay, you could do, like n point amplitude, now I can do n+1 to higher loops. So you really need, we always want to keep that in mind, that we'd like to make previously impossible computation possible. And Yara illustrated this in his talk already with some examples. So I'd like to show this, picture from Zvi. So this program lies on two pillars. So on one hand, you have structure, beauty, etc. But on the other hand, we always need to remember that we want to have always the results for physics, which are useful outside our particular model. Okay, great. So without further ado, let me just tell you what is the status and what is the amplitude. Okay, so for the purpose of this talk, we're going to think of amplitudes as a function of some variables, and I will have more to say about functions and variables. And each amplitude is going to be characterized by three numbers. You also saw that in Yara's talk. So number of points, which is n, number of loops, which is L. So for example, this is how many loops? How many loops? No, not from Andrei, but from maybe anybody, want to ask maybe a graduate student in math. Oh, undergraduate. Thank you, Andrei. Okay, very good. So this is an example of a 7-point amplitude. So number L, number of loops. So seven loops, and this is n. Yeah, so Matteo knows this is 6. That's very good. So number n. So for this graph, number n is 6. Number L is 7, and then there is k. Okay, so k. So you can label each external line with a plus and minus. So k tells you how many pluses and how many minuses you have. So the slang is as follows: when you have all pluses or all but one minus, so one minus all pluses and no pluses, such amplitudes are 0. And the first time you can have something non-zero is when you have 2 minuses and no pluses, and that's called MHV. If you hear the slang, now you know what that is. And then you can, so n, and then we talk about NMHV, n square MHV, etc. So that's that number k that also appeared in Yara's talk. So for example, so this is MHV. NMHV would be minus, 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 plus, plus, plus. Okay, so that's the terminology. So number of points, number of loops, and we call this helicity k. So let me just quickly overview how much has been computed. So physicists worked very hard in the last 15 years to compute those objects. And again, I mean by computing, I mean an answer, a function of variables, the result of an integral. So let's start. So let's start going and increasing number of points. So start with 4 points and 5 points. So such amplitudes been known to all loops. So again, for 4 points, and 5 points, you can only have MHV because minus, minus, plus, 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 or the parity conjugate. So those have been known for 20 years now due to the work of Van Dixon and Smirnov. And then, so recently, due to the progress in the field, the 6-point MHV has been computed, and that's a result from last year by Dixon and his graduate student, Andy Liu, have been computed through 8 loops. So it's a very, very impressive result. Now, if you start increasing n for 7 points, these are known through 4 loops. So this is the some of the review where you can learn about the methods. Then, if you start, so that these are just MHV. Now, if you start increasing n, they're only known still through 2 loops, due to still old paper by Simon Carol Huot. And then so if you go to 8, MHV are known through 3 loops, so the references are here, and 8 and 9 NMHV are known through 2 loops. Okay, so that's the status, but of course we want to solve, eventually we want to have a formula. So what do I mean solve the theory? We want to have a formula for all n, all L, all K. So we want just an answer. Maybe Mathematica, whatnot, we want to have an answer for a final manageable answer with a structure. So, but that's where physics, this is where physics stands due to the various advances in this field. So let me just say a few words about.
Question, like you said, compute, for example, if the answer takes 100 pages.
That's okay. That's good. As long as it's on the compute and the function, like polylog of some, yeah, that's good. In fact, some of these results are indeed a Mathematica file. And indeed, I think I'll say more about it, but indeed, if a large group of mathematicians looked at this, I think they would be able to make progress, because a lot of these are just mathematical. Even so even beyond going to this table, already in 8 loops, etc., it's Mathematica file, but it's good enough. But I think you can't go to next order without better understanding, the huge Mathematica files. Any other questions? Okay, then let me say a few words. How have this been computed? So most of these results are due to Lance Dixon, who gave a colloquium about maybe at the beginning of this program, and his collaborators. So it's a work over the past 15 years. And so nobody computes it like by doing writing integrals and integrating and no. So the way this is computed is by something called bootstrap, where you do the following: you kind of guess an answer, you make an ansatz, you write down your answer as a linear combination of some functions. So I will say more about it, what kind of functions of what kind of arguments, and then you start imposing various physical constraints on those functions, such as symmetry, something called collinear limits, so these amplitudes obey various physical properties, so such as collinear limits, multi-region kinematics, etc., etc. So these are just some tables. So these are some tables for 6-point amplitudes up to 6 loops. So you start with this many functions, and then you start imposing symmetry, and you see that number becomes smaller. So this is for MHV, and this is for NMHV, etc., etc. And then you do it by Mathematica or Maple in Lance's case until you get a unique answer. So that's how these computations are done.
What does it 0, 0 mean?
0 means that you've solved it. That these 2 constraints already solve it uniquely. Yeah. So you don't need to go further. Yeah. So for higher, you need more.
Are the numbers dimensions?
No, the numbers are the number of functions you need.
Oh, there's like a literal number, not
Literal number of functions. Yeah. Special functions. And this work, I have to say, progressed. The better they understood the structure of the answer, if you go back, the smaller basically the numbers are now, right? So they started with something bigger, and then they understood that, okay, it's better to impose this condition and then that condition. And so it's very, very important to understand the structure of what you're doing before actually engaging in these calculations. But this is probably the most impressive thing that there is in this whole program. So they were able to get Mathematica file, which just gets you an answer, final answer for the integrated amplitude up to the 8 loops. Okay, so now let me say a few words about some of the physics and important ingredients which enter into this calculation. So, of course, I noticed majority are mathematicians, and I wasn't sure. So this is maybe mostly aimed at skeptical physicists, because there was something a program called Amplitudes Bootstrap is not new. It's something that people physicists in the 60s or something worked on. And for example, there's a book from the 60s called Analytic S Matrix. And people tried very hard to construct scattering amplitudes based on a few physical principles and understanding of the analytic structures. So when you say, why couldn't they do it? So let me just right away say, what are some new ingredients? So the three main ingredients. So first, we are not talking about arbitrary quantum field theory. We're talking about this particular n equals 4 Young-Mills theory. The second important point is that the variables, which Jarl already said a few words about, that usually these amplitudes are functions of momenta and polarization. So now we're going to be talking, and I will have a slide on that. They would be functions of momentum twistors. So it's very important to write down the correct variables that these amplitudes depend on. So the momentum twistors are important new gradient number one. And then there's something called symbol, which I will also tell you about. So we're not going to be talking, well, we can be talking about the final function, but there's something in between, the actual final answer. There's something called symbol of those special functions, which captures the singularity structure of those amplitudes, and I will explain that momentarily. So as I said, so we're going to think about, again, the cartoon again, we're going to think of these amplitudes, so n, remember nkl, the parameters, but cartoon-like slide, these are functions of some kinematics. So now I'm going to have a slide on each. So the kinematics is going to be, kinematics and then, kinematics and functions. So kinematics is going to be described by momentum twistors. So you've seen the slide from Jarl already. So in quantum field theory, we label particles with their momentum. Now, if you have it's very important that you have massless momentum. You can write something called spin helicity variable. So you can write your 4 vector as a product of 2 spinners. And then what you do, you go to something called dual coordinates. And this is where this dual conformal invariant, again, I'm skipping a lot of things, becomes important. And eventually you associate to each momentum. So to each momentum, there's a dual coordinate x. And then to each x, you can associate a line. Now finally you see z's that appeared. And these are called momentum twistors. And these are lines at P3. So now every time I'm going to talk about kinematics, the variables that my amplitudes are going to be depending upon are going to be, so these z's, and there'll be n of them, and they live in P3. And we will be everywhere, we can take everywhere you'll see, next slide, the brackets, and these are just the determinants of these 4x4 matrices. So that's the kinematics. So everywhere, I will be quickly switching to these brackets. So, and then the second point, so these are variables, so they live in GR4N. And then the functions, what kind of functions do we encounter? Well, that's again the special property of this theory. So at L loops, remember there was N, there was L, and there's K. At L loops, it turns out that the functions have uniform transcendentality, and the transcendentality is 2L. So for example, at 2 loops, you will be talking about transcendentality for functions. So what's transcendentality? So pi and log transcendentality 1, log squared lead 2, pi squared transcendentality 2, and so on. So first, you have the complexity goes like this. You have log, then you can talk about polylogs. And then you can talk about generalized polylogs where, remember the definition of polylogs, you have T, and now you can put arbitrary parameters A. And then starting at 10.2 loops, K equals 3, and squared, and squared MHV, you're going to encounter something called elliptic polylogs. This is where you have, instead of t minus a, you would have like square root of some cubic polynomial. So you'll have some elliptic curve. So the frontier of this is a whole, I guess, community of people now. The whole, I guess it's a whole community of people trying to understand the space of functions, and in particular, these elliptic polylogs. They even have their annual meeting now called elliptics, maybe for the past 5 years or something. Yeah. So that's. But I'm going to stop in here. I'm going to stop at generalized polylogs. So that gives you kind of hopefully a flavor of what we're talking about. So we have this Grassmannian, and we're looking at these polylogs and generalized polylogs living on this Grassmannian.
My question.
Uh-huh.
That 8-loop example that you mentioned, is that through which functions is that?
Yeah, through the generalized polylogs, yeah.
No elliptics.
That one was MHV. That one didn't have elliptics, yeah. That's MHV. So this starts at n squared, yeah. Okay, very good. So, but I will have some explicit example momentarily. So, okay, so amplitudes are functions of some kinematic variables. Okay, very good. Now we are going to do, okay, so that's cartoon. We're going to kind of like take the next order kind of iteration. So next complicated object I'm going to define, which is symbol. Okay, so I'm not going to talk about general functions and general kinematics. I'm just going to focus on for this particular talk. I can give a whole talk on functions, and there's a lot of, again, work and interesting things. I will just be talking about variables, this kinematics. And we would want to know, so restricting to kinematics. And moreover, I will be talking about symbol, which I will have a whole slide on the next page. These are arguments of these polylogs, which encode the location of singularities for these amplitudes. So what is a symbol? Okay, so this is this is a slide with an example of what the symbol is. Not a rigorous, just for those who haven't seen it. Hopefully, you'll know walk out of this talk. I hope knowing what the symbol is. So for those who know, they pay attention. So let me just introduce these two definitions. So if you have a log function, define the symbol of a log as the argument, and then a symbol of Lie2 defined as a 2 tensor product. So symbol of Lie2x is -1 minus x tensor x. Okay. So for generalized polylog functions, I will have the recursive definition or general recursive definition on the next slide. But already with these two things in the box, you can already see why it's so important and so useful. So this is something that Sasha Goncharov introduced and taught us about it. So for it, kind of what it does, it trivializes your polylog identity. So for example, you know that this is an example of an identity. Lie2 of x plus Lie2 of minus x is this. So what you can do is just with this definition, you can see, okay, Lie2 of x, what's my symbol? 1 minus x tensor x. And then what's the symbol of Lie2 of minus x? It's okay, minus, so this becomes plus x, tensor minus x. Then there's some properties that symbol, so you can forget about, you can always multiply by a constant. And there's some properties this object obeys. And you can write it as, 1 minus x times 1 plus x is 1 minus x squared. So there you go, you can write it like that. And then using some other properties of the symbol, you rewrite it as x squared and you put a half. Okay? So this line immediately shows you that the symbol of this is the same as this, and that's nothing but the symbol of 1/2 Lie2 of x squared. So that's kind of the probably simplest example of what the symbol is good for. Okay? So is that possible to Smita and ask Smita? Is it okay? Yeah. Okay. Very good. So more generally, the situation is like this. So as I said, if you have an L loop amplitude, you can express it in terms of generalized polylog of weight to L, which means that's essentially the definition of generalized polylogs of weight L to L. So you could write it df as f d log of something, and you can, and so on. So then the symbol can be defined recursively as basically the arguments which appear in this log. Okay, so if I just now use this, if I take, so I take g of Li2, and g of Li2 is minus log 1 minus d log z, you see? So symbol by this definition is just minus 1 minus z times z. Okay, that was the same that I showed on the previous slide. So now all these arguments that appear in these logs, so the collection phi, that's what I mean by symbol alphabet. Okay, so when I say symbol alphabet, symbol letters, so this would be, so for you know, see, this would be like this. So this the amplitudes will be complicated multivariable functions, so there will be, you know, a lot of things happening, and so they encode what they do. These letters. So there's a collection of letters, and I'm going to show you immediately what these letters are for each amplitude. They encode the singularities of our amplitude. So let me just show you some slides. So this is again from physics. Knowing the notion of this symbol, somebody computed for you. Imagine somebody did hard work and computed for you the function of some variables, and now I'm just going to write down for you what those letters are. And then, of course, because you're mathematicians, to you it's going to be trivial. What is the mathematical structure of this? But for us, was very non-trivial because we didn't know anything about classical algebras. So you physicists, imagine, and you start computing it, and somebody brings you this 6-point alphabet. And that's what so that's physics. That's a result of a computation. At 6 points, you get 15 letters. Okay, A plus 1, B, C. Okay, at 7 points, you're going to get 49 letters. So these are just flukers. And then, I should have had the definition. And these are quadratic. Okay, they're on the next slide. Okay, so sorry, I should have added it. This expression is just quadratic expression in these flukers. Okay, so from result of physics computation, you have 6 and 7 point symbol alphabet described by these letters. Okay, so these I've explained to you, the brackets, and that's that. Of course, if I talk to you, Lauren, before I, you know, when somebody computed, she would have told me immediately what probably should recognize this, but it took some time, yeah, for us to reach. Then of course, when we showed this to Sasha, he immediately told us what these are, and then we, you know, started learning cluster algebras, and of course everything started making sense. But okay, 6 and 7, good. So I will say a few words later on. So what is known from physics? So also what's known is 8-point symbol alphabet is known, and 9-point of alphabet is known, and that's a result. So this has been computed by some of his students, and I have a list. And Mark will say more about this list. So 8-point, just keep in mind, 8-point and 9-point is known, and these are, you start, it's still no good problem to fully understand what's going on here. Very good. So let me again say a few words. How were these computed?
Sure, the question.
Mm-hmm.
Can you define symbol for arbitrary flat number?
Well, we deal with this so I only know functions. So for functions, I know how to define. So you have to.
Well, for example, you have a differential equation with regulars is like some polynomials, and then there's some numerator structures. I don't want to get too.
So yeah, maybe yeah. So I can only tell you that there's still work. There only recently the symbol. So multi-polylogs is. This is the definition, but for even elliptic polylogs, this is like 5 years old or something. Only people started to explore those. I can tell you about that, but I don't think any more generalities have been explored yet. Okay, so let me just again tell you. Yeah, actually, I was surprised that he was even showing this. So for 6 points, physicists Deluca, and Smirnov computed the amplitude. Right. So, and this was a long time ago, and the expression was given in terms of some long 17 pages of Gottschalk polylogs. So then what happened is, you know, I was a junior faculty at Brown, and we were looking at this, and how do we, you know, if we ever going to solve anything about n equals 4 Young-Mills theory, we'd better simplify this formula, because if 6 points is like that at 2 loops, there's no way any progress could be made. So then we were like, okay, these are Goncharov polylogs, and kind of, I come from Russia. I kind of knew, as a mathematician. So we emailed Sasha this expression out of blue. He's like, "Who are you? What are you?" He said, "No, I can't help you. I can't help you with this. This is some algebra, some computer work. Go away." So okay, fine. But luckily, in a few days, it was a few days, maybe a few hours, he said, "Okay, maybe let's meet." This is like, us three people come to math department. Who are you? So remarkably, he talked to us, so we were very happy. And so he taught us all this. It's been set many meetings for over a year. So we learned about this symbol, and we were able to simplify this expression to this simple function. So again, these are the real computations that physicists do. And from this, you can extract now the letters that I'm talking about. Okay, very good. So for next, maybe I could probably skip this. For higher points, the technique is different for these computations because the integrals, so these people, to look at Donald Smirnov, so Smirnov is the expert in evaluating integrals. He has books on evaluating integrals. So they evaluated integrals in doing so. It's a really hardcore. No further integral has been actually evaluated. But what people have been doing is Simon Caron-Huot invented this very clever trick of relating an L loop amplitudes and any at endpoints and K to a previously L-1 loop amplitude, but higher points and higher n+1. And this is called the Q-bar equation. And with this technique, very, very clever technique, they were able to compute, so Song, Hees, and Student, they were able to produce those lists. Okay. So for physics, so again, the takeaway for physics, we know something about those lists to up to 9 points. Okay. But of course, I wouldn't be here, what we'd like to know, what is the mathematical description of this symbol alphabet? And of course, if you seen the 6 and 7 points, you would recognize it immediately, and you would see that those letters are not just arbitrary letters, and these are cluster coordinates for the Grassmannian cluster algebra. This would be explained in my next slide. So again, this is what I'm focusing on. But then there was, maybe in the last 5 years, a lot of, so then you saw I had a list of 8 and 9, and you can go, and I think it's interesting still to go, I think it would be interesting to more mathematicians to look at those lists and see more structures. I think if more people look at it, there'll be more progress. So, but there were various explanations, and so some of this due to our group, some of due to Thomas Lamb, who's here, and my student Li Cheng will tell the connection to tensor diagrams. So there's various ways to understand those, but let me just say quickly about these 6 and 7 points. So again, it's not surprising to you, surprising to us. Once those computed, the letters are nothing but cluster coordinates of the Grassmannian cluster algebras, GR for 6 and GR for 7. And indeed, we've heard a very nice introduction by Christina. So you remember she had so GR for 6 cluster algebra, that's the same as A3, that's a quiver diagram, frozen nodes are in the box. So what you do, so this is A3, so you mutate on each node and you produce 14 quivers. I think this is a Wikipedia even, and you get 15 cluster coordinates, and these are the cluster coordinates for A3 cluster algebra, and these are indeed the coordinates that appear in physics. So that matches a 6-point symbol alphabet computed for physics. Good. So next is 7. So for 7, so she explained to us that GR for n, you start with a 3 by n minus 5 grid. So here you start by 3 by 2 grid. So this actually by mutation, this could be shown that it's just the quiver could be mutation equivalent to the E6, something which looks like E6 decay diagram. And indeed, there are many more quivers, and there are, if you mutate, you get 49 cluster coordinates, and there are which are Plukers and then quadratic expressions. So this was quite remarkable, so this was the first connection between something we compute in physics and a concrete connection. So something we compute in physics, these scattering amplitudes for two loops, 6 or 7 points, and plus the coordinates. Okay, very, very concrete. Okay, so very good, but we would like to prove this. We would like to prove this to all loops. Okay, so people can only compute this up to 3. So eventually, so the problem that we've been, obsessed about for the past, Mark has been obsessed since 2016, is to prove this, that to high loops, that's all you can get. So you can say, well, wait a minute, you were just telling me that Lance Dixon and his collaborators computed this to 8 loops. Yes, they computed it, assuming that there are no other singularities. So it's an input to the ansatz. You start with those letters for 6 and 7, and then you impose the physical conditions, and then you get those high loop amplitudes. But how do you know there's nothing else? So that's the second part of my talk, which I will be quite brief because but there's some fun things, some things we learn. Let me just say a few. So I have to stop in 10 minutes, right?
Yeah, 2:50, but you started a little bit late.
Yeah, okay. I will, yeah. So maybe I pause. It's a good time to pause if any questions. So at least hopefully I explained what the status and so physicists computed 6 and 7 up to 2 and 3 loops. And eventually we want to try to prove this to all loops with maybe some methods, which I will explain. Any questions? Okay, so then I will explain some of our attempts to do that. And this is based on a paper, actually 2 papers. So first is our former student, Luc Lipsteo, who is now in Edinburgh, and our former postdoc, the student of NEMA, actually, Akshay Girish-Pushrikant, who is now in Oxford. So what we've tried to do is, again, and what we've tried to do is not just limited to, actually, it turns out it's not just limited to n equals 4 Young-Mills theory, and it's actually true for any massless planar Feynman integrals. So again, this I'm repeating, we'd like to provide a better foundation for the bootstrap, and we want to investigate what can we say about the singularity structure of Feynman integrals in general, with hoping to prove that for 6 and 7 points, there's nothing else. Okay, for that, there's a tool in physics, which is due to Landau, and there is a small community of physicists now trying to apply these techniques to various and reinvent various ways. There's better ways to compute the integrals, but there's a well-known technique due to Landau paper 1959. So if you have any Feynman integral, which I will have an example on the next page. So given any Feynman integral, which, yeah, again, so you can write down a set of kinematic constraints that are necessary for the appearance of a polar branch point in the integrated function. And so maybe I do it with this example. So let's look at the integral and this 5-point integral. So you have momentum P1, P2, P3, P4, P5, and you're integrating over internal momentum Q. So this is simplest loop integral from quantum field theory. So Landau equations for this integral state that what you want to do, you want to put each propagator on shell. So these are the conditions which are here. So you associate, so to each internal propagator, it's on shell, plus you have something like Kirchhoff condition. You associate the parameter, alpha parameter, to each internal line, and you write down an equation like this. So just think of it as some set of known fixed algebraic equations, which is the following. If the statement is that, okay, you write down some known equations called Landau equations, and if you can find a solution for alpha, that means, so that would impose some constraints on this external momentum. Okay, so for this system to have a solution for various alphas, it turns out the following condition has to be true. And then this is in terms of momentum. And then if I rewrite this in terms of momentum twistors, this boom gives me this condition. And so this is the way to rederive those simple letters from these algebraic equations. Okay, so there's well-known techniques. Now it hasn't been applied. So now you can say, okay, so what do you want to do with this? Well, The integrals for n equals 4 Yang-Mills theory have only been explicitly written due to work of Jake and Yara and Nima maybe 10 years ago. So of course, we immediately went on and tried to apply this to those, but that's not what I'm going to tell you about. So I'm going to tell you about something interesting. So it turns out, so this was for arbitrary graph. It turns out that Landau singularities, so meaning solutions to this system of equations that I just presented, are those only subsets of not arbitrary graphs, but special graphs. And these are something called ziggurat graphs. I don't know, we haven't heard much about it. Basically, one of our students Googled it, right, Mark? Is that the history? Yeah. So the ziggurat graphs, anybody heard about ziggurat graphs? No? Okay. These are the following. So for 4 points, nobody heard ever of ziggurat graphs. No, not from my paper. But okay, so there is there's a thesis by this person. That's where he introduced. So nobody checked anything, but basically, let me tell you the notion of ziggurat graphs. So for 4 points, start with a graph like that. And now it's going to be, you're going to go flip by one. So from this graph, you go to next one by building a block here. You see? So you have 4 points, and now you have 6 points. So white, there's nothing to do with line graphs or anything. The white just means that these are external variables. So this is 4 points, and these are 6 points. And then you continue. So like this ancient structures in Mesopotamia, you see? It's like you start with graph and then add more and then more. If you're interested, I think this is very, very fascinating. Okay, so and then so that's for even. For odd, you do the same. So this is 5 points, and then you add this. So from this one, you add this block and you continue. So these are called ziggurat graphs. Okay. So why should you care about them? Well, it turns out that first of all, any graph could be reduced to this ziggurat graph by the sequence of moves. And these are moves that are that comes from basically some kind of E&M. There's a certain, so I will have graphs and examples on the next slide. So it turns out that, yeah, so any graph, I think it's a thesis by this person. And so any graph, it turns out, could be reduced to ziggurat by these moves. And then secondly, Mark and his student, they showed that Landau equation is actually invariant under these circuit moves, moduli some details that I will have on the next slide. So let's start with an example. So you start with 6 point ziggurat, right? So then these are the these are the sequence of moves that were on my previous slide. So it's going to be as follows. So you can replace a triangle like this. So remember, okay, maybe this is getting too technical. So triangle is delta y transformation triangle. You can replace with delta like that. So you have, so this is a triangle that you take, and then you replace it with y, et cetera, et cetera. You do this kind of moves, and you reduce the 6 point ziggurat graph to a graph like that, okay? And then you can take this graph and you compute Landau singularities of this graph, okay? So not arbitrary graphs. Normally for amplitude, you do arbitrary. So it turns out that matches exactly this, the solution to the Landau equations for this graph matches the 6 point symbol letters, okay? So that gives one hope, because so that's not arbitrary graphs, you know, so then that gives one hope that there's a systematic way to derive these to all loop orders, okay? Okay, moduli some things. So then with Luke, we started playing more, revisited this question for 7 points. So we very slow, we go by example, until we hopefully one day understand something. But okay, for 7 points, this is a sequence of moves. And by this sequence of moves, you can reduce it to this graph, okay? And then you can go and try to write down Landau equations for this graph and compute the letters. So I'm just presenting the result of Luke's hard work. So we find agreements with all but 7 letters from the leading graph. And then we went on to subleading, and then we start finding surprises. So at the next subleading order, we were finding new letters that the outside heptagon, outside 7-point alphabet. So that's I guess where we are. And okay, so we analyzed all of these graphs one by one. For the other, so there are 9 of them in total, and for the others, there were no other new letters. So this is again, I mean, it's working towards the proof of these letters. You know, it's the next. Again, as I said, you always want to go further than what's known. So yeah, so that's the result. And of course, you can say so. Well, I mean. So do they appear in amplitudes? We hope not. So we were hoping that maybe one can do the bootstrap and add those letters. Suppose you do the bootstrap with these letters, you probably get, nobody did this calculation, but I think if somebody does this calculation, they hopefully will find that the coefficients in front of these new letters are 0. But if not, if there exists another solution to the bootstrap equation with non-zero coefficients, I think that would be probably interesting, and one has to do a lot more work. So again, this is what it is. And of course, you know, we at the end are interested in the final result of the amplitude and not individual graphs. So the other, so there are other, I don't call it problems, but technical issues with this. There are some solutions that violate the delta Y equivalence, but in a controllable way. So one can go in principle with a big computer and go and see all those things. Oh yeah, so we also did did this. We compared the particular leading singularity of the scale integrals to the leading singularity computed via its own shell diagrams, and we were not finding extra letters there. So it's not a proof, but it's a recheck maybe. Yeah. So with that, I think I will I'm on time. So I'll just summarize again. So we were hoping to derive the 6- and 7-point alphabet to high loop order. And so we went to the next complicated case, solve Landau equations for 9 3-loop 7-point graphs. And we found 2 graphs with singularities outside the 7-point alphabet. So, and it's important to understand this better, as this is I keep emphasizing over and over again, and this is an important input to the Bootstrap program. And, you know, there's a lot of things to do. So all high N, or higher loops, beyond polylobes, beyond planar, beyond equals 4, etc., etc. But I will just stop here with this modest result. Oh.